Okay, let's get to work on another kind of problem now. Let's say that we know what an electric field is, but it's not a constant electric field. It's 350 times x plus 130 in the j, or the up direction, newtons per coulomb. So I've drawn a box. I'm going to say that the corner of my box is at the origin. Here's our coordinate system x, y, and z. Two things we'd like to find out: what is the net electric flux through the box, and what is the charge in the box. So our strategy here is we're going to find the electric flux using the integral of E dot dA. We'll see that our box has 6 sides, so we're going to do this 6 times, one for every face. Then to get our net electric flux, we're going to add it all up, and then we'll have the total. After we find the net electric flux, we're going to remember that flux is equal to charge enclosed over epsilon naught. That'll let us find the amount of charge that is inside the box. Okay, let's get started. So we want to find the flux for each face. We have to pick a face to start on. I'm going to say let's pick the left-hand face, or let's pick the right-hand face, because that's going to be easier to draw. So we'll start with the right face. On our right face, what do we know? We know that at the right face, x is equal to 1 centimeter, 0.01 meters. If I know what x is, then I know what my electric field is. So my electric field is 350 times x plus 130, that's in the j direction with units of newtons per coulomb, equals 133.5 newtons per coulomb in the j direction. That's going to be constant. You see, we don't have any x dependence here because we're at a constant value of x. So now my net electric flux on the right face is the integral of E dot dA equals, I'm going to take my E outside because my E is constant. You're allowed to do that even if you do have your scalar product. You can put your dot inside or outside. I put it inside, maybe I should have put it outside. E dot the integral of dA. The integral of dA is just the area A. So I've got E times A. A means the area vector of my right-hand face. So the area is the size of the area, which is the length times the width. In the direction of area, area is straight out of the face. So in this case, that's the I direction. Okay, what have I got here now? E is 133.5 J newtons per coulomb. My area is 0.01 times 0.01. That gives me 1 times 10 to the minus 4. That's meters squared in the I direction. So I'm dotting this with 1 times 10 to the minus 4 meters squared I. I've got a j dot I here. J dot I equals 0. So my net electric flux through the right-hand face equals 0. That makes sense because my electric field vector points up, my area vector points out. Those two guys are perpendicular. There's not going to be any flux. Okay, let's do the left-hand face next. For my left face, I have x equals 0. So now I'm looking at this face. My x equals 0, which tells me that my electric field is equal to 350 times 0 plus 130. That's in the j direction with units of newtons per coulomb, equals 130 j newtons per coulomb. My area, or why don't we write down our Gauss's law first? My net electric flux is equal to the integral of E dot dA. E is a constant, so it comes out front. The integral of dA is A. Equals, my area now points to the left and it has the same magnitude. So I've got my electric field vector times my area vector minus 1 times 10 to the minus 4 meters squared I hat equals 0. Okay, net electric flux through the left face is also 0. Still makes sense because the electric field is up, the area vector is left. Okay, which face will we look at next? Why don't we do the top face next? The top face is going to take a little bit of work, so I think I'll go to a fresh sheet of paper. Okay, I'll redraw my box. Okay, that box got a little bit squishy, but it's kind of box-like. Grab a different color for my top face. So for my top face, it's a little bit different because x is not constant anymore. On my top face, x varies. So top face x varies from 0 to 1 centimeter. So for my electric field vector, I can't put in a value for x. I've got to stay with my 350 times x plus 130 in the j direction with units of newtons per coulomb. I'll write down my flux. Flux is the integral of E dot dA. This time my E is not constant. I cannot take it outside. I'll put my E in right here, 350x plus 130 j. I'm going to drop my units just for the sake of convenience. Okay, what about my dA? That's the hard part. dA means a little area of, a little element of the area vector. So if I was going to pick a little element of the area vector, I would pick a long, thin rectangular strip across my top, because I would know my strip would have a length equals 0.01 meters, and I would know it had a width of a little bit in the x direction, which would be called dx. And then the direction of my little area vector would be straight up, because areas come straight up out of the face. So my dA would be my length, 0.01, times my width, dx, in my direction, which is straight up, or j hat. Okay, now I've got my area vector, so I'm dotting that with my area, 0.01 dx. J hat, so what I've got here is the integral 350x plus 130 times 0.01 dx, j dot j. Let's do a few things in one line here. 350 times 0.01 gives me 3.5, that's times x. 130 times 0.01 gives me 1.3. Those are both times dx. J dot j, that's equal to 1. And let's put in the limits of my integral. Remember I said x varies from 0 to 1 centimeter, so 0 to 0.01. You probably are familiar enough with integrals that you would just do this without splitting it up, but technically you're supposed to split it into two, 3.5x dx plus 1.3 dx, 0 to 0.01. That integral gives us 3.5 x squared over 2, evaluated at 0.01 and 0, plus 1.3x evaluated at 0.01 and 0. 3.5 times 0.01 squared over 2 minus 3.5 times 0 squared over 2 plus 1.3 times 0.01 minus 1.3 times 0 to give us 0.01318. Okay, now for my bottom face, I can do all of this again exactly the same, or I can take advantage of a little bit of symmetry here. So on my bottom face, so this is my bottom face down here, x varies from 0 to 1 centimeter. My electric field is going to be 350x plus 130j. My dA, I'm going to pick my area element to be a little strip of the surface with a length of 0.01 meters, a width of dx. This time my area element on the bottom face points straight down. So on my bottom face, dA equals minus 0.01 dx j hat. So the only difference in all this work is that instead of plus 0.01, I have minus 0.01. Therefore, my flux through my bottom face is equal to minus 0.01318. Okay, so there's my top and bottom done. I've got left and right done. Next we have to do front and back. The front and back face will be pretty similar to the top and bottom face. Okay, make sure my paper is in view. Okay, so let's do the front face. Very quickly draw my box again. Okay, front face means I'm taking the front face. So my x varies from 0 to 0.1, so this is the face I'm looking at. That means that my electric field is not constant. It's 350x plus 130 in the j direction. My area element I am going to pick as a little rectangle again. It's got a length L, which is 0.01 meters. The width of it is a little bit in the x direction, dx, and the direction is straight out of the front face. So there's my dA. My dA for my front face is equal to the length times width, 0.01 times dx. The direction is straight out of the face, that is the z direction or the k hat. Okay, let's get going with the flux. Net electric, or the electric flux through the front face is the integral of E dot dA equals to 350x plus 130j dotted with my dA, which is 0.01 dx in the k direction. You see here I've got j dot k equals 0. The scalar product between perpendicular vectors equals 0. Then my last face I have to take care of is my back face. My back face is this one back here. Take the same area element, which is a little strip. This time the area sticks straight back out. So for my back face, my dA equals 0.01 dx, the length times the width. This time it's in the negative k hat direction. My electric field is exactly the same because the x value still varies and it's in the same direction. So I'm going to get exactly the same result for my back face as I had for my front face, and my net electric flux equals 0. Okay, now we'll circle back around to what the question was. What is the net electric flux through the box? So my net electric flux is all of those values added up. So let's get all those values. We'll just have a look as we add them up. So there's the flux through the right face, which is 0, plus the flux through the left face, 0. The flux through the top face, the flux through the bottom face, flux through the front face, and flux through the back face. 0. So the net electric flux through that entire box is equal to 0. There's my net electric flux. That tells me that any electric field line goes into the box also comes back out. Okay, what was the last question? What is the charge inside the box? So if we remember that net electric flux equals Q enclosed over epsilon naught, that tells us Q enclosed is flux times epsilon naught equals 0. There can't be any charge at all inside that box.